All right, moving on now to the precordial leads. Remember, these are the leads that actually look at the heart in the transverse or horizontal plane. So they're going to consist of 6 separate electrodes placed on the torso. So these are also going to be unipolar leads, meaning there's one electrode, and the negative end of that lead is the electrical center of the heart. They're going to record activity in the horizontal plane. The positive end is going to be where you put that electrode. The negative end is the center of the heart. And these are the 6 precordial leads. So V1 through V6. And what I've done is put the landmarks where the electrodes go. So V1, fourth intercostal space. So that's starting at the top of the ribs and counting down. You always want to put them between the ribs and the intercostal spaces. So just to the right of the sternum, and then V2, same height, just on the left side of the sternum. And then when you put these electrodes on, generally after you put V1 and V2, you put V4 next. And that goes at the left midclavicular line. So middle of the clavicle, down at the 5th intercostal space. And then the next one you would generally put on is V6. And that would be same level as V4. So you find where you put V4 and you make sure you're going directly horizontal with that. And it would be on the left side of the body. So like the left mid-axillary line, which is basically the left side of the body. And then you can go back and put V3 on, which is directly between V2 and V4. And then V5, you can put pretty much directly between V4 and V6, but it does have its own landmark also. So left anterior axillary line. So just envision about where your armpit is, the front of your armpit, and put it at the same level as V4. So what that looks like is something like this. So V1, V2, you put V4 on next, which would be here in the 5th intercostal space. And then V6 goes all the way on the side. And then you could put V3 between these, and then V5 between these. And this is probably a better picture here showing you that. So these are the precordial leads, and this kind of gives an idea of how they're looking at the heart. So by looking at this picture, what I want to do is kind of take you through those same phases of the cardiac cycle. So going with atrial depolarization, septal depolarization, ventricular depolarization, and then ventricular repolarization. So I'm going to put the same kind of little arrows, but remember now we're talking about the horizontal plane. So during atrial depolarization, if we kind of look at each of these leads, and again, we may not completely agree on all of these, but if this arrow is the direction of the depolarization, you can see like in those leads, V5, V6, you're definitely going to get an upward deflection. Whereas V1, it looks like it might be perpendicular. So you might get that biphasic or down. The rest of these just may be variable. I mean, it looks like from this picture they'd probably be upward deflections, but you just got to consider the electrode placement and also the exact placement of the heart. The exact placement of the heart in individuals can differ slightly. Then septal depolarization. So I put the arrow in there again. You see this. So you can see that now, like in V6, you would definitely get a downward deflection because it's going away from the positive end of that lead. Whereas in V1, it looks like it's going definitely towards the positive electrode, so you get upward. Then ventricular depolarization. I put the arrow where the direction would probably go, and you can see kind of similar effects. So like V5, V6, definitely upward deflections. The rest of these probably upward. Like when you talk about V3, V4, once you get to like V1, V2, it looks like it's almost perpendicular, so you might get some downward or biphasic waves. And then lastly, the ventricular repolarization, basically opposite direction, but remember with repolarization, everything's opposite. So everything that we said for the waveforms for the depolarization is pretty much the same for the repolarization. So now we're actually going to put some names on these waveforms. So some of this you may be familiar with from other classes if you've learned about basic EKGs before. But P wave. The P wave is generally the first wave we're going to see for a cardiac cycle. It reflects atrial depolarization. And if we take it a step further, we can actually say the first part of that P wave reflects the right atrium, the second half the left atrium. The reason we know that is because the depolarization starts at the SA node and goes across in a right to left fashion, and that is that's assuming it's a normal heart and a healthy heart. But that we can actually, you'll see this later in the semester, we can actually determine if there's a problem with the right or left atria by looking at different parts of the P wave. And so in reality, you get this waveform, and then a split second later, the atria contract after they depolarize. So characteristics of a normal P wave: smooth and round, just like this. Relatively small. I put 2.5 millimeters in height or less, and less than about 0.12 seconds in duration. And we'll talk shortly about how to determine the time length of each of these waves. All right, then we have a QRS complex. This is probably the most complex part of an EKG waveform. So there's 3 possible waveforms, a Q, an R, and an S wave. And not every QRS complex is going to have all 3. Just always remember that, but we still call it a QRS complex. So the Q wave is always negative, represents depolarization of the septum. And R wave is the first upward deflection of the QRS complex. And if there are 2 positive deflections, you'll see this in a few minutes. The second one's called an R prime. And then the S wave is the first downward deflection following an upward deflection. So if there are 2 downward deflections following an R wave, the second would be an S prime. That is not common at all. But an R prime is sometimes, you will see that, a lot more of that. But so not every wave is going to have a Q, an R, and an S, but some will. Some may only have an upward deflection. That would just be an R wave, but we still call the whole thing a QRS complex. So we'll go through some examples on this next slide. But so the R and the S waves represent the depolarization of the ventricles as a whole. So if we name these waveforms, so this would be an RS R prime, because the first upward deflection is the R wave, and a downward deflection following an R wave is an S, and then we have a second upward, so this would be the R prime. This would just be a QR, because the first downward deflection is a Q, and then R. This would just be an R wave. This would be a classic QRS, downward, upward, downward. This would just be RS, and then this is a weird one. This is the one that throws everybody off. You may just look at this and say, well, why this should just be called a Q. But this is the only thing you get, you call it a QS wave. So if it looks like this, we call it a QS wave. All right, so QRS complex characteristics. This is important. So the whole QRS complex should be less than about 0.1 seconds. We can extrapolate that to 0.12, and there's a reason I'm saying 0.12. You'll see that shortly, but 0.12 and below is considered pretty normal. The Q wave generally should be small, so less than about 25% of the R wave. So if we're looking at this, you can see this Q wave is less than 25% of this R wave. So if you get a really big Q wave, like about once it approaches like half or so, or greater than 25% of the R wave, that's problematic, and that generally signifies that there's damage to the heart somewhere. Oftentimes it's due to scarring of the heart due to a heart attack, and we call those pathological Q waves. So we'll talk more about that this semester. So keep in mind, a Q wave should be relatively small. So the T wave is the next waveform you'll see. This reflects ventricular repolarization, and it should be going in the same direction as the bulk of the QRS complex. So this is mostly upward in the QRS, so the T wave is going upward also. That's important to see. And then lastly, I probably won't talk about this again all semester, but there's another wave called a U wave that's possible. You hardly ever see it, but it's possible. I just feel like I should tell you about it. So it would be after the T wave, so kind of like this or this. Not commonly seen. It's thought to be excess repolarization. Not unusual, but just continued repolarization of some of the Purkinje fibers. All right, so if we put all this together, and I'm just going to talk right now about lead 1, atrial depolarization. So notice for lead 1, I put the positive here, negative here, and that's because that's the classic lead 1. So we get atrial depolarization. Let me go back. So atrial depolarization, which would go across kind of like this, we would get an upward deflection, so that would give us the P wave. Then we get septal depolarization, which comes back across like this. That gives us that little Q wave. Then we get the bulk of the ventricular depolarization, which goes down like in this direction, and that gives us that big R wave. And then we get ventricular repolarization, which goes back this way, but in repolarization, the waveforms are reversed, so that gives us the T wave. We could also talk about this in the precordial lead, so I'm going to focus on V5 just because it's a major lead and we can all see it. So atrial depolarization, which kind of comes like this, you're going to get that upward deflection. Septal depolarization comes back across like this, so you're going to get that downward Q wave. Ventricular depolarization goes back this direction, so you're going to get the upward R wave. And then ventricular repolarization comes back this way, but everything is reversed, so that gives us the T wave. All right, so a couple other things before we talk about some calculating heart rate and some other things. So there's this concept of R wave progression. So when you look strictly at the precordial leads, the R wave should gradually get bigger as you go from V1 towards V5. Oftentimes you'll see it all the way to V6, but if this is what the textbooks will tell you. If you just look at the R waves from V1, V2, V3, V4, V5, they're gradually getting bigger as you go from V1 towards V5, and then V6 is a little bit smaller. It's not uncommon to see the biggest one in V6, but the point here is that you should see this R wave progression. If you don't see that, that usually signifies something's wrong. So you should always, in a normal EKG, you always want to verify that normal R wave progression. All right, so segments and intervals that you can calculate. So a segment by definition is a line between two waveforms. So like this red line would represent a segment. An interval, on the other hand, includes a waveform along with a segment. So we'll run through some of the more common ones that we'll measure. So the RR interval is the interval between two R waves. And you could also calculate a P to P interval, and that would be between the P waves. So the RR interval is most commonly used just to give us our ventricular rate, or which is going to translate to our heart rate. All right, the PR segment, this is an important one. So the PR segment, actually the PR segment is less important than the PR interval, but they're similar, but the PR interval is going to include the waveform also. So the PR segment is just this little segment right here. This is often used to just make sure that the ST segment is at the same height or a similar height. The PR interval, on the other hand, is a little more important. We always want to measure the length of the PR interval. So time-wise, it should be between 0.12 and 0.2 seconds. And there's a quick way to figure that out, which we'll talk about shortly. So 0.12 to 0.2 seconds. If it's longer than that, that means it's too long and that's abnormal. If it's shorter than that, that's also a problem. So we always want to verify that the PR interval is in that time range. 0.12 to 0.2. And we'll talk about how to calculate that quickly. The ST segment gets a lot of publicity because it's commonly used to determine whether or not the heart is ischemic or not getting enough blood flow. So the ST segment is this little segment right here between the QRS complex and the T wave. And the point where the QRS and ST segment meet, like right here, this is called the J point. And the amplitude of this segment is really important. So we want to compare it to this PR segment like I was saying earlier. And if it's too low, we call that ST segment depression. If it's too high, we call it ST segment elevation. Both of those are not normal, and we'll talk about the implications of each, but long story short, the ST segment depression generally means that the heart is ischemic. And that's probably the most common indicator of heart disease during exercise. So if you're exercising and exerting yourself, if your heart becomes ischemic and they see ST segment depression, that's a good sign that there's some significant cardiovascular disease and the heart's not able to get enough blood flow. All right, the QT interval, less commonly measured, but I'm going to talk about it anyway. So beginning of the QRS all the way through the T wave, it's going to change with the heart rate. So you can correct it by heart rate, and that's what this equation's for. We're not really going to focus on this. But a normal QT interval is generally less than half of the RR. So you can see that's the case here. And what does it signify? If it gets too long, that represents a lengthened refractory period of the heart, and it kind of puts the heart in this vulnerable position where it's at risk of going into some type of dysrhythmia. All right, so to recap on the segments and intervals, you can see the ones we talked about here. PR interval, this is just the P waveform. What's not shown here is a PR segment, which would just be from here to here. You get the QRS complex, the QT interval, the ST segment, and the T wave. All right, when we look at EKG paper, it looks like graph paper. So that's the next thing we need to talk about. So what you're going to see, and you'll see some pictures of this coming up, is basically graph paper, and you're going to have small and large boxes on it. So each of the tiny boxes, the small boxes, are 1 millimeter in width and height. The large boxes are basically 5 of those, so 5 millimeters in width and height. And thus, if you're printing out an EKG or watching it go across a screen, the horizontal axis of that paper represents time. So just envision like graph paper flowing through like a printer, and the printer's printing out an EKG. So we want to make sure that paper speed is at a constant rate, because that's when we measure these intervals, we want them to know what we're looking at time-wise. So the normal paper speed on an EKG when it's printed out or going across the screen is 25 millimeters per second. And if we're using that normal speed, 5 large boxes are going to represent 1 second of time. So another way to look at it is one large box is going to be 0.2, and then one of those tiny boxes, which is 1 millimeter by 1 millimeter, is going to represent 0.04 seconds. So what that looks like is this. So graph paper wise, if we'll just start small here. This is the graph paper I was talking about. This is classic EKG paper. So each one of these tiny boxes is 1 millimeter. So 5 of those from here to here would be 5 millimeters. So if we have that 25 millimeters per second paper speed, this one small box represents 0.04 seconds of time. Thus, 2 small boxes would be 0.08. 3 would be 0.12. 4 would be 0.16. And then 1 big box or 5 small boxes is 0.2. And then, like we said here, 1 second is basically 5 of those big boxes. So hopefully now you're kind of seeing like how you can quickly determine what a normal interval is, like the PR interval. We said it should be between 0.12 and 0.2. That means it should be between 3 and 5 small boxes. If it's longer than that, that's too long. If it's shorter than that, that's too long. So here's another quick picture just to kind of show you the time. All right, so that's time is the horizontal axis. The vertical axis is voltage or amplitude. So there is a conversion for voltage. It's not commonly used. So mainly when we're talking about amplitude of waveforms, we just report them in millimeters. And 1 millimeter is one small box. So, for example, one of the things that we might want to know the elevation of is the ST segment, or depression of. So if you see it that it's depressed a little bit, you could quantify that by saying, oh, there's 2 millimeters of ST segment depression in this EKG. So the vertical axis, we generally report it in millimeters, and the horizontal axis is what we report in time. All right, I'm going to finish up here talking about heart rate. So you should be able to look at an EKG printout and calculate the heart rate. And the way to do this is probably the most accurate way I should start with. We're going to talk about 4 ways to do this. Count the number of small boxes between 2 consecutive R waves and divide into 1500. So 1500 is kind of like a magic number right here. So for example, if you had 2 R waves here and we counted 20 small boxes between the 2, we would just divide 1500 by 20. We get 75. That's the heart rate. This is the most accurate way to do it. However, as you can tell, in real time, it would be really hard to do that. So we do have other ways to do this. But if you have a printout, an EKG printed out, and you want to be as accurate as possible, this is the way to do it. So other methods include, if you just want to focus on the large boxes, you can do the same thing. Count the number of large boxes between 2 consecutive R waves and divide into 300. So if I went back to this example, I could look at these large boxes, and the problem is it's not likely that these R waves are going to fall on the end or beginning of a large box. So 1, 2, 3, almost 4 large boxes. So we would do a similar thing, and 300 divided by 4. So it should give us a similar number, not quite as accurate, but similar idea. Then we have methods that would be more so used in real time. So if you were watching an EKG go across the screen and you didn't have a representative of heart rate and you needed to look at the waveforms to determine heart rate, one method, this is a very rough way to do it, but the 6-second method. So if you look at this EKG paper, there's 3-second markers. So as the paper goes across, 3 seconds, and then there's another little tick mark at another 3 seconds. So 2 of those represent 6 seconds. So if you count the number of R waves in that 6-second period, just add a 0 to it, or multiply it by 10, and you would get a rough estimate of the heart rate. So let's say you had 7, like we see here. That means there's a rough estimate of the heart rate would be 70 beats per minute. Then another way to do it, which is also a relatively rough way to do it, but in real time you may need to do it. Select an R wave that falls on a dark vertical line, kind of like we're doing like this. So on the beginning of one of those big boxes, and then you number the next few big boxes: 300, 150, 100, 75, 60, and 50. And you look at where that next R wave falls. So in this case, we're starting with this one, and then the next one falls on 1, 2, 3 big boxes over. So we're going to say the heart rate in this case is about 100 beats per minute. If that next one landed here, we would say it's about 60 beats per minute. So again, kind of a rough and dirty way to do it, but in real time, sometimes you just need an estimate of the heart rate. All right, and then lastly, determining the rhythm and regularity of an EKG on an EKG. So rhythm refers to the site of origin of electrical impulses. If it's a sinus rhythm, that means the beat originates at the sinus, at the SA node. Junctional rhythm means it originates at the AV node or the bundle of His. So a ventricular rhythm would originate in the ventricles. So we can determine the rhythm by the rate and the shape of the complexes. So we know, for instance, that the ventricles have a slower rate than the SA node. So if the rate is really slow, that gives us an idea that it might be a ventricular rhythm. And also the shape. This is something we're going to get to as we go through the different rhythms, but like ventricular rhythms, the QRS complexes have a completely different shape than a normal sinus rhythm. So you can look at the shape and the rate. And then regularity refers to the consistency of the timing. So ideally, we have a regular heart rate, which basically means that there's a consistent distance between the QRS complexes or the P waves. So if it's regular, the intervals will be generally within 10% of each other. So if you're seeing like really, really short QR, or let's say really, really short RR intervals, followed by really, really long RR intervals, that's not a regular rhythm. So taking it a step further, if the variations between the longest and shortest RR intervals is less than 4 small boxes, which is 0.16 seconds, we call it regular. If it's more than that, we call it irregular. So what you might see, and sometimes even in healthy hearts, people have irregular normal or irregular resting heart rates. And that's just because their heart rate is so slow. So people with low resting heart rates, maybe like in the 40s and 50s, there's a lot of variability in their RR intervals. And that's in itself not necessarily a bad thing. It's just when you get this too much of this, especially at even higher heart rates, that's when it becomes a problem. So if there's a repeating pattern of irregularity, we could call it irregular, meaning like if it's kind of going through a pattern where it's changing, but it's a consistent pattern, we could call it regular, irregular. And if there's no pattern whatsoever, we call it irregular.